Light, moving at the universal speed limit, can travel once around the surface of our Sun in about 14.5 seconds. That is the circumference of the star that warms our planet, traced by a single photon in less time than it takes to read this sentence aloud. There is a star in our own galaxy where that same journey takes about 6 hours. Not seconds. Hours. A photon moving at the speed of light, faster than anything in the universe, would take longer to circle the surface of that star than most people spend awake on a slow afternoon. And that star, 6-hour photon and all, is not the biggest star we have measured. It is not the second biggest. It is not even, by some honest counts, in the top 5. Tonight we are going to walk through the largest known stars in the universe. We are going to meet a star most people have already seen with their own eyes, a star most people have never heard of, and a star that, in November of 2024, became the first star outside our own galaxy ever to be photographed up close. Along the way, we are going to learn why the question of which star is biggest keeps changing, and why the most honest answer is also the one our imagination finds hardest to hold. If you find some peace in these slow journeys through the cosmos, a quiet like and a subscribe help this channel keep walking these roads with you. Now, settle in. Let your shoulders drop. We begin. Before we meet any individual star tonight, we need to talk about the question itself. Because the question, when you look closely, is stranger than it seems. If you asked 100 different people on the street, which is the biggest star in the universe, most of them would not know. The few who had a guess would probably name a star they had heard once in a documentary. WOH G64 perhaps, or WOH Canis Majoris, or Stephenson 218. The names would sound confident. The answers would sound settled. They would be, in almost every case, out of date. The honest story of which star is biggest is not a story of a single answer. It is a story of a long, slow argument between observations and measurements, conducted across more than a century of astronomy, with the title changing hands roughly every decade or so. Sometimes more often than that. In the 1930s, the largest star known was thought to be one of 2 candidates, depending on which paper you read. Epsilon Aurigae b in the constellation Auriga, or VV Cephei A in Cepheus. The estimates for these stars at the time placed them at perhaps 2,500 times the radius of our Sun, or even larger. Those numbers were based on the best techniques of the era, which were not very good. We did not have accurate distances. We did not have interferometry. We had basic photometry and a great deal of educated guessing. By the late 20th century, the title had shifted. WOH Canis Majoris, a red hypergiant in the constellation Canis Major, became the new candidate. Early measurements suggested it might be enormous. Some papers in the 1980s and 1990s gave it a radius of 2,000 or even 3,000 times that of the Sun. Those numbers too turned out to be wrong, or at least incomplete. The star is large, but it is not as large as those early estimates suggested. The history continues decade by decade. Mu Cephei, KW Sagittari, NML Cygni, Westerlund, 126, WOH G64. Each of these stars, at some point in the last 40 years, has been named in popular sources as the largest known star in the universe. Each of these stars, when measured more carefully, has been revised. Sometimes the revisions made the star larger. More often, the revisions made the star smaller. The single most dramatic example of this revision is WOH G64. WOH G64 is a red supergiant in the constellation Scutum in our own galaxy. For many years, popular sources cited WOH G64 as the largest known star, with a radius of about 1,700 times that of the Sun. The number appeared in countless documentaries, science articles, and educational videos. It became the standard answer when people asked which star was biggest. Then, in 2018, the European Space Agency released the second dataset from a mission called Gaia. Gaia is a space telescope dedicated to measuring the precise positions and distances of stars. Its measurements of stellar parallax are the most accurate ever made, and when Gaia's data was applied to WOH G64, the distance to the star turned out to be smaller than astronomers had previously thought. Smaller distance means smaller actual size. because the star's apparent size in the sky is what we measure, not its physical size. If a star is closer than we thought, the same apparent size translates to a smaller physical reality. UY Scuti after Gaia came in at about 755 times the radius of the Sun, less than half of what was previously claimed. Still very large. Still a red supergiant, but no longer in the top tier. UY Scuti, which had worn the crown of largest known star for years, was quietly demoted. This is the pattern. The new measurement, a better instrument, a refined model. And the list shifts. The current best candidate for the largest known star is depending on which paper you trust most. Either a red supergiant in the Large Magellanic Cloud called WOH G64, or a red supergiant in our own galaxy called Stephenson 2088, or perhaps something else again depending on how the science evolves between now and the time you watch this video. We are going to walk through several of these candidates tonight. We are going to look at how big they actually are, what makes the measurements difficult, and why the answer to a question that sounds so simple has turned out to be so persistently slippery. But before we meet any individual star, we need to be clear about what we're even measuring. Because the word big, when you apply it to a star, does not mean what most people think it means. It is worth pausing for a moment before we move on to feel the shape of this history. The list of stars that have, at various points, held the title of largest known is itself a small tour of 20th century astronomy. Each entry on the list reflects what the instruments of its era could see and what the models of its era assumed. Each entry, when better instruments came along, was reconsidered. In the early years of the 20th century, the largest known star was thought to be Betelgeuse, simply because it was one of the few stars whose angular diameter could be measured at all. Albert Michelson and Francis Pease in 1920 used a primitive form of interferometry at Mount Wilson Observatory to measure the apparent size of Betelgeuse. Their result was the first time anyone had directly measured the size of a star other than the Sun. It was a major achievement. It also placed Betelgeuse briefly at the top of the list. Other stars followed. Antares was measured shortly after. So was Mira. The technique that Michelson and Pease pioneered was slow, difficult, and limited to the brightest, nearest, largest stars. But it produced, for the first time, real measurements of stellar size rather than rough estimates. As the 20th century progressed, the techniques improved. The estimates grew. Stars further away, dimmer in apparent brightness, came within reach of the new methods. The list of contenders for largest expanded. By the mid-20th century, candidates like VV Cephei A, Epsilon Aurigae B, and KW Sagittarii were being discussed. Some of the radius estimates from this era are now considered extraordinarily inflated. Numbers like 3,000 or 4,000 solar radii were thrown around for certain candidates. Most of those numbers have not survived. The next major shift came with the launch of space-based instruments. The Hipparcos satellite in 1989 gave us parallax distances for thousands of nearby stars with unprecedented precision. The Hubble Space Telescope in 1990 gave us imaging without the atmosphere getting in the way. Both contributed to a slow tightening of stellar measurements throughout the 1990s and 2000s. But the real revolution for our story came from Gaia. Gaia, launched by the European Space Agency in 2013, was designed for one main purpose: to measure, with extraordinary precision, the positions, distances, and motions of more than 1 billion stars. The mission has been releasing data in stages. Each release improves the precision of the catalogue. The second release, in 2018, was the one that demoted UY Scuti. Subsequent releases have continued to refine the distances to many of the stars on our list. The effect of Gaia on the largest known star question has been generally to bring the numbers down. Several stars that were once thought to be enormous have been revised to merely large. UY Scuti is the most famous example, dropping from 1,708 to around 755 solar radii. But other stars have been revised similarly. NML Cygni, once thought to be one of the largest, has come down. Various candidates have come and gone. The current top of the list, the position currently occupied by WOH G64 and Stephenson 2088 in some uneasy combination, reflects the state of measurement as of the mid-2020s. New data will probably continue to refine this. Some current contenders may shrink. New candidates may rise. The list will look different in 2030 and different again in 2040. This is not because the stars themselves change. The stars are doing what they have always done, slowly burning through their late phases over millions of years. The list changes because our techniques change. We see better, we measure more carefully, we learn what we got wrong, and we correct it. The history of the largest known star is, in this sense, a history of human knowledge rather than a history of stars. The stars are out there. Their actual sizes are what they are. We are simply, over the centuries, getting slightly closer to seeing them as they actually are. When you ask, in everyday language, how big something is, you usually mean its size in physical space. How tall, how wide, how much room it takes up. A truck is bigger than a car. A whale is bigger than a dolphin. Big is a single, intuitive concept. We feel it in our bones because our experience of physical objects has trained us to recognize it. Stars do not work this way. When astronomers say a star is big, they could mean any of 4 different things, and these 4 things do not correlate in the way you might expect. They are, depending on the conversation, separate properties of the same object. The first meaning of big is mass. How much matter is in the star? How many protons and neutrons and electrons add up to make the thing? Our Sun has a mass we call 1 solar mass. Some stars have less. Some have far more. The most massive stars known have well over 100 solar masses, sometimes approaching 300. The least massive stars have less than 1/10 of a solar mass. Mass varies across an enormous range. The second meaning of big is radius, or equivalently, diameter. How far the star's surface extends from its center. This is what we usually mean when we use the word size in everyday conversation. It is the thing you would measure with a ruler if a star could fit on your desk. Radius also varies enormously across stars, from neutron stars only about 20 kilometers across to the giants we're discussing tonight, which are billions of kilometers across. The third meaning of big is volume, which is closely related to radius but not identical. Volume scales with the cube of the radius, so even a moderate change in radius produces a very large change in volume. A star twice the radius of the Sun has 8 times the volume. A star 1,000 times the radius of the Sun has 1,000,000,000 times the volume. The fourth meaning of big is luminosity, how much energy the star emits per second, how bright it shines in absolute terms. This is what astronomers measure most directly because brightness is what reaches our telescopes. From luminosity combined with temperature and distance, astronomers work backward to figure out the other properties. Here is the strange thing. These 4 properties, mass, radius, volume, and luminosity, do not move together in the way an everyday object would expect them to. A star can be massive but small. A star can be enormous but light. A star can be moderately massive but absurdly luminous, or very massive but moderately luminous. The relationships depend on what kind of star it is, what phase of life it is in, and how it has evolved. When you and I say a star is big, we almost always mean radius or volume. We mean a star that takes up a lot of space. We mean the kind of star where, if you placed it at the center of our solar system, its outer atmosphere would extend past the planets we know. That is the meaning that comes naturally to the human mind, because it matches the way we think about everyday objects. A big star, to us, is a star that occupies a lot of cubic space, but when astronomers talk about a star, they often have to be careful which meaning they have in mind. A red supergiant might have only 15 times the mass of the Sun, but a radius 1,000 times larger. That is a star that is, by mass, fairly modest, by radius, enormous, by volume, almost incomprehensible. The reason this matters is that the stars we're going to meet tonight are mostly red supergiants. They are stars in the late phases of their lives, when they have finished burning hydrogen in their cores and have moved on to burning helium. During this transition, the star inflates dramatically. The outer layers of the star expand, sometimes to many hundreds or even thousands of times the original size, while the inner core contracts and grows hotter. The star becomes much larger by radius, but its mass does not change very much. Some material is lost through stellar wind, but the bulk of the star is still there. It has just been spread out across a much larger volume. This is why a red supergiant is, in a sense, mostly empty. The outer layers of a star like VY Canis Majoris or WOH G64 are so diffuse that if you could somehow stand on them, you would not stand on anything at all. The density is comparable to the air at the top of Earth's atmosphere. There is no solid surface. There is no liquid surface. There is only a gradient from somewhat thicker gas in the interior to thinner gas at the edges, with no clear boundary in between. When we say one of these stars is 2,000 times the radius of the Sun, we're talking about the radius at which the gas becomes thin enough to be transparent, the radius at which light from inside the star finally escapes into space. That is a useful definition, and it is the standard one astronomers use, but is exactly the same as the radius of a planet which has a solid surface you could land on. A red supergiant has no such surface anywhere. This is the first reason the question of which star is biggest is harder than it sounds. The thing we are measuring, the outer edge of the star, is itself fuzzy. It is not a fixed boundary. It is a statistical average of where the gas runs out. Different measurement techniques applied to the same star can give different answers for the edge depending on what wavelength of light you use, what model of the atmosphere you assume, and how the gas happens to be distributed on the day you measure. So when we say a star is big, even after we have agreed that we mean radius, we are still talking about a quantity that has fuzz around it. There is no precise number. There is a measurement with an error bar, and the error bars are sometimes very large. To really feel why the four meanings of big do not move together, let us look at two specific stars. One that is small but extremely massive. One that is enormous but only moderately massive. They are both extreme. They tell us in opposite directions what stars can do. The first is called R1136A1. Its name is a label, not a name. It comes from a catalogue of stars in a region called R136, which is the bright central cluster of the Tarantula Nebula in the Large Magellanic Cloud. R136R1 is a Wolf-Rayet star. That is a particular kind of very hot, very luminous, very massive star in the final phases of its life. It has spectral signatures that show ionized helium and nitrogen and carbon with little hydrogen, because the star has already burned through most of its outer hydrogen layers. R136 is by current estimates the most massive star known anywhere. Its mass is somewhere in the range of 190 to nearly 300 times the mass of our Sun, depending on which measurement technique and which model you use. 2022 measurements with the Zoro-Speckle Imager on the Gemini South Telescope settled on a value around 196 solar masses. Older measurements from Hubble Space Telescope spectroscopy went higher, around 215 solar masses. More recent atmospheric modeling has pushed the figure up again, into the 250s or higher. But here is what makes R13601 interesting for our story tonight. Despite being the most massive star known, R13601 is not enormous. Its radius is about 42 times that of the Sun. That is far larger than the Sun itself, but it is far, far smaller than the red supergiants we're discussing. R136A1 is mostly compact. It is incredibly dense, incredibly tense, incredibly hot, incredibly luminous, and incredibly massive. But it does not take up much physical space. It is a fierce, small, bright object. A diamond, not a balloon. By contrast, consider a star like UY Scuti, the one we mentioned earlier, which used to be cited as the largest known. UY Scuti has a mass of only about 10 solar masses. 10. Compared to 1136A1's nearly 300. UY Scuti is, by mass, a very ordinary massive star. There are many stars with similar mass. There are even more stars with greater mass. But UY Scuti's radius, even after the Gaia revision, is about 755 times that of the Sun. UY Scuti is a balloon, not a diamond. It has a relatively modest amount of matter, spread across an enormous volume. This is what stars do. They can take any amount of matter, from about 1/10 of the solar mass to perhaps 300 solar masses, and they can choose, over the course of their lives, how to arrange that matter. They can be compact and hot, or diffuse and cool, or anything in between? The same amount of mass can be packed into a small fierce star or spread across an enormous gentle one. The choice is made by the star's age, its composition, and its internal physics. It is not a choice we make. It is a choice the laws of physics make, and we observe the result. For our purposes tonight, this means one thing very clearly. When we ask which star is biggest, we are asking about the balloon stars, not the diamond stars. We are asking about volume and radius, not about mass. The biggest star by mass is something like R1 Ron 36A1. The biggest star by radius is something very different. They are not the same kind of object. They are not in the same competition. If Orion 6 Appalled were placed at the center of our solar system, its surface would reach almost halfway out to Mercury. Mercury would orbit just outside it, badly toasted but technically outside the star. That is enormous compared to the Sun, but small compared to what is coming. The stars we are about to meet are the balloons. They are the diffuse, cool, swollen giants. They're the stars that, if you place them where the Sun is, would swallow planets. Some of them would swallow only the inner planets. Some would swallow everything out to Mars or Jupiter. The largest of them would swallow Saturn, and one of them perhaps would reach even further. We are going to walk through them now, from the more familiar to the more strange. We will start with a star you have almost certainly already seen with your own eyes, on a winter evening, even if you did not know what you were looking at. If you live in the northern hemisphere, and you step outside on a winter evening, anywhere away from the worst of the city lights, you can see Betelgeuse with your own eyes. You do not need a telescope. You do not need binoculars. You only need to know where to look. Find the constellation Orion. Orion is the hunter, with 3 bright stars in a line forming his belt. The constellation is easy to spot in winter, low in the southern sky from northern latitudes, high in the sky from the equator and the southern hemisphere. Around the belt, 4 bright stars mark the corners of the hunter's body. The upper left corner, as you look at it, is a noticeably reddish star. That is Betelgeuse. It is, by some accounts, the right shoulder of the hunter. Depending on which mythological version you read, it has been a shoulder, a knee, an armpit, or simply the brightest red dot in that part of the sky. The Arabic name from which we get Betelgeuse means, very roughly, the hand of the giant, or the shoulder, depending on translation. It has been called Betelgeuse, or some version of that name, for at least 1,000 years. Betelgeuse is a red supergiant. It sits about 640 light-years away, in a region of the galaxy that has produced many of the most familiar bright stars of the night sky. The light you see from Betelgeuse on a winter evening left the star around the time the Mongol Empire was conquering most of Asia. The photons have been traveling toward your eye for 640 years. When they finally arrive, they enter your pupil, hit your retina, and trigger the sensation of a red point in the sky. The radius of Betelgeuse is somewhere between 764 and 1021 times the radius of the Sun. The wide range in that figure tells you something. Even for a star this nearby, this well-studied, this familiar, we cannot agree on the radius to better than about 30%. The reason is that Betelgeuse is variable. It pulsates. Its outer layers swell and contract over periods of months and years, sometimes throwing off shells of dust, sometimes brightening and dimming in patterns that astronomers are still trying to understand. If Betelgeuse were placed at the center of our solar system, its surface would reach at minimum somewhere past the orbit of Mars. At its maximum extent, the surface would push out toward the orbit of Jupiter. The exact distance depends on which measurement you take and when you take it. Mars would be inside the star. Earth would have been swallowed long before Mars. Venus, Mercury, all of the inner planets, gone, cooked away, vaporized, absorbed into the gas of the outer atmosphere of a star that, here on Earth, looks like a single faint red dot in the sky. In late 2019 and early 2020, Betelgeuse did something that briefly captured the attention of the world. It dimmed, not by a little, by a lot. Over the course of a few months, the star lost more than half of its normal brightness. From Earth, with the naked eye, it became noticeably dimmer than its usual self. People who knew the sky well noticed immediately. Astronomers around the world turned their instruments toward Betelgeuse to figure out what was happening. For a brief, dramatic period, there was real speculation that Betelgeuse might be about to explode. Red supergiants do explode. Eventually, they end their lives as supernovae, briefly outshining their entire galaxy, leaving behind a neutron star or a black hole and a vast expanding nebula of debris. If Betelgeuse were to go supernova in our lifetime, it would be the brightest event in the sky in centuries. It would be visible during the day. It would cast shadows at night. It would be a once-in-many-human lifetimes event. The dimming, the speculation went, might be a sign that the star was approaching that moment. Mass loss accelerating. Outer layers unstable. The final convulsions before collapse. The dimming was real. The interpretation was wrong. By mid-2020, careful observations had revealed what had actually happened. Betelgeuse had thrown off a cloud of dust. The cloud, ejected from the star's surface in some kind of convective burp, had drifted into the line of sight between us and the star. The dust absorbed and scattered the visible light from Betelgeuse, making the star appear dimmer to our eyes and to our telescopes. The star itself had not changed dramatically. The dust had simply gotten in the way. This was an important lesson. Betelgeuse is one of the few stars whose surface we can actually resolve with current telescopes. The Hubble Space Telescope has imaged it. The Very Large Telescope in Chile has imaged it. Recent observations have shown actual features on the surface, large convective cells, hot spots, cold spots, regions where material is rising and falling. We can, in a limited way, look at Betelgeuse and see surface structure. That is a remarkable thing given that the star is 640 light-years away. But even for Betelgeuse, this close, this bright, this well-studied, the radius is uncertain to about 30%. The 2019 dimming event made the uncertainty even worse because the dust cloud distorted measurements for months afterward. And Betelgeuse, in the end, is not unusually large among red supergiants. It is moderate. It is famous because it is close and visible to the naked eye. The other stars we are about to meet, the ones that exceed Betelgeuse in size, are much further away, much fainter, much harder to study. Their measurements are correspondingly less certain, but they are also almost certainly larger. Take a moment before we move on. The next time you are outside on a winter night, look for Orion. Look for that reddish star in the upper left. That is a red supergiant. It would swallow the orbit of Mars. It is 640 light-years away, and it is, by every careful measurement we have, not even in the top 10. There is something else worth saying about Betelgeuse before we move on. The star, like many red supergiants, pulsates. Its outer layers expand and contract over rhythms that can be measured in months and years. Sometimes the rhythm is regular. Sometimes the slips, drifts, recovers. Astronomers have been watching the brightness of Betelgeuse vary for more than a century. The records, when you plot them, show a complicated dance. Several different cycles, layered on top of one another, producing a pattern that is almost regular, but not quite. The longest of these cycles is around 400 days. The shorter ones are around 200 days or so. There may be longer cycles too, on timescales of years to decades, that we are still trying to characterize. This pulsation matters because it tells us something about the inner structure of the star. Red supergiants pulsate because their outer layers are unstable. The pressure that holds the star up against its own gravity is finely balanced, and when that balance shifts, the layers swell. As they swell, the gas cools. As it cools, it becomes less able to support the weight above it. The layers fall back. The fall warms them. The warming pushes them back out. The cycle repeats. A red supergiant is, in this sense, breathing. Slowly, painfully, with the kind of rhythm that you would feel if you placed your hand on the chest of a sleeping giant. The great dimming of 2019 and 2020, the event we discussed earlier, may have been partly a pulsation event combined with a dust ejection. Some of the dimming was caused by the dust cloud blocking our view, but some of it may also have been the star itself in its breathing cycle happening to be at a contracted, cooler phase at the same time. Two effects, layered on top of each other, producing one dramatic dimming that briefly made the world wonder if Betelgeuse was about to explode. It was not. It will. Eventually, but not in 2020. Probably not in this century. Possibly not in this millennium. The honest timescale for Betelgeuse's supernova is somewhere in the next 100,000 years with very large error bars. It will happen. We do not know when. What we do know is that when it happens, the supernova will be one of the brightest events in human history. Betelgeuse at 640 light-years would briefly be as bright in our sky as the full moon. Or brighter. Bright enough to cast shadows at night. Bright enough to read by. Bright enough to be visible during the day as a brilliant point of light next to the sun. But not tonight. Tonight, Betelgeuse is still there, pulsating quietly, breathing through its long final phase, 640 years of light away. It will be there next winter, and the winter after, and probably for many winters yet to come. If you have stayed with us this far, take a small moment. The journey we are on tonight is long, and we have only just begun to climb. A quiet like and a subscribe help this channel keep walking these roads with you. Thank you for being here. Let us continue. Just above Betelgeuse in our slow climb up the ladder of size, there is a tier of red supergiants that are larger than the hunter's shoulder, but still visible to the naked eye, still familiar to people who have spent time learning the stars. Two of these are worth meeting on the way. The first is Antares. Antares sits in the heart of the constellation Scorpius, the Scorpius. From northern latitudes you can see it low in the southern sky on summer evenings. From the southern hemisphere it climbs higher and stays out longer. The name Antares comes from ancient Greek and means something like the rival of Mars or against Mars. The star earned this name because of its colour. Antares is reddish like Mars, and like Mars it has a hue that catches the eye even in a sky full of other lights. Ancient observers noticed the similarity. They named the star for it. Antares is a red supergiant, slightly cooler and slightly larger than Betelgeuse. Its radius is about 680 times that of the Sun, give or take. That is, in absolute terms, very large, but by the standards of the stars we are climbing toward, Antares is modest. If Antares were placed at the center of our solar system, its surface would extend to about the orbit of Mars, similar to Betelgeuse. The two stars are in many ways cousins. They are both red supergiants. They are both relatively nearby. They are both visible to the naked eye. They both pulsate slowly. They both will, in some unknown future, end their lives as supernovae. Antares is closer to its end, in some estimates, than Betelgeuse is. Some models suggest Antares may explode within the next few 100,000 years. Others suggest the timeline is longer. The honest answer is that, for any individual red supergiant, we cannot predict the moment of its supernova to within better than thousands of years. The stars are old. They live for millions of years in their stable phases. They burn through their late phases in tens of thousands of years. By human standards, we are watching a single still frame of a very long movie. The second familiar giant is Mauchifay. Mauchifay does not have the popular fame of Antares or Betelgeuse, but it has, among astronomers, a particular reputation. It is one of the largest stars visible to the naked eye. In September of 2024, the International Astronomical Union officially named it the Garnet Star, formalizing a nickname that had been in use for more than 200 years. The nickname comes from William Herschel. Herschel was one of the most famous astronomers of the 18th century. He discovered the planet Uranus. He catalogued thousands of nebulae and clusters. He was the first to correctly describe the shape of our galaxy, and in 1783, while sweeping the northern sky with his telescope, he came across Mauchifay and was struck by its colour. He wrote in his published observations that it was of a very fine deep garnet colour, a most beautiful object, especially if you looked at a white star first and then turned your telescope to it. The name stuck. For nearly 2.5 centuries, astronomers called Mauchifay the Garnet Star after Herschel's description. In 2024, the IAU made it official. Mauchifay is a red supergiant in the constellation Cepheus, which sits in the far north of the sky. Its radius is estimated at somewhere between 970 and 1,650 times the radius of the Sun. depending on the source and the technique. That is a wide range, again because mu Cephei is variable and the measurements have evolved over time. But even at the lower end, mu Cephei is significantly larger than Betelgeuse or Antares. At the higher end, it would extend, if placed at the center of our solar system, beyond the orbit of Jupiter. Mu Cephei is also famous for being one of the most luminous stars visible to the naked eye. Its total light output is roughly 350,000 to 475,000 times that of the Sun. Most of that light, however, is in the infrared. Our eyes only see the visible portion. If our eyes could see infrared, mu Cephei would be one of the brightest stars in the sky. As is, it appears as a relatively modest reddish point around magnitude 4, easily visible from a dark location, but not striking from a city. It is, by every accounting, a star that should be much more famous than it is. It is larger than Betelgeuse. It is more luminous than Betelgeuse. It carries a name given by William Herschel himself, ratified by the IAU 2 centuries later. And yet, because it does not sit in a famous constellation like Orion, most people have never heard of it. Antares, mu Cephei, Betelgeuse, these are the giants you can see. The next stars we are going to meet, you cannot see. They are too far. They are too far. They are too faint, despite their size. They are, in some cases, hidden behind dust. They live in parts of the galaxy where light from the inner clouds blocks any direct view. To see them at all, we need telescopes, and even with our best telescopes, what we see is barely a dot. Their size, their nature, their existence as enormous objects, we infer from indirect measurements. We do not see them. We deduce them. That is where the story starts to get harder and stranger. There comes a point, as you climb the ladder of stellar size, where the comparisons start to break. Up until now, we have been talking about stars that, if placed where our Sun is, would swallow Mars or maybe push out toward Jupiter. Those are large, those are extraordinary. But the human mind can, with some effort, still hold the picture. We know the inner planets. We can imagine a star that fills that region. The star we are about to meet does not fit in that picture. VY Canis Majoris sits in the constellation Canis Major, the Great Dog. It is in the same patch of sky as Sirius, the brightest star in the night sky. But where Sirius is close and brilliant, VY Canis Majoris is far and faint. It hides at the edge of visibility around magnitude 7, just below what most people can see with the naked eye. To find it, you need a small telescope. To study it properly, you need much more. The star was first catalogued in 1801 by a French astronomer named Joseph Jerome Lalande. Lalande did not know what he had found. To him, it was simply another faint reddish point of light, recorded in his catalogue of southern stars. The understanding of what VY Canis Majoris actually is, the depth and strangeness of it, did not arrive for nearly 2 more centuries. Today, we know that VY Canis Majoris is a red hypergiant. The word hypergiant is not a casual one. It is a formal classification. It refers to red supergiants that are, even by red supergiant standards, unusually large and unusually luminous. There are only a handful of confirmed red hypergiants in our galaxy. VY Canis Majoris is the most famous of them. Its radius is about 1,420 times that of the Sun. Let us sit with that number for a moment. 1,420. If we were to take our Sun with its surface that light circles in 14.5 seconds and somehow stretch it outward, increasing its radius without changing anything else, we would have to make it nearly 1,500 times larger to reach the size of VY Canis Majoris. The volume change is even more dramatic. Volume scales with the cube of the radius, so VY Canis Majoris by volume is roughly 3 billion times the volume of the Sun. 3 billion suns by volume could fit inside it, with room to spare. If we placed VY Canis Majoris at the center of our solar system, its outer atmosphere would extend beyond the orbit of Jupiter. Earth would be inside the star. Mars would be inside the star. The entire asteroid belt would be inside the star. Jupiter, with its 60+ moons and its faint rings, would orbit inside the outer atmosphere of the star, swept along through diffuse gas at temperatures of a few thousand degrees. That is what 1500 solar radii looks like in real space. And the photon. The photon you imagined earlier, traveling around the surface of the Sun in 14.5 seconds. If we put that same photon at the surface of VY Canis Majoris, it would take 6 hours to complete one circuit. 6 hours. The same photon, the same speed, the same universal limit, just a much, much larger surface to travel around. That is the star we're talking about. The measurement of VY Canis Majoris that gives us this radius came from a specific paper published in 2012. The lead author was an astronomer named Markus Witkowski, working with collaborators across several European institutions. They used an instrument called the Very Large Telescope Interferometer in Chile, equipped with a tool called AMBE. Interferometry combines the light from multiple telescopes, treating them as a single, much larger telescope. The result, when it works, is a level of resolution that no single telescope could achieve on its own. Witkowski's team applied this technique to VY Canis Majoris. They measured the star's apparent diameter on the sky in tiny fractions of a second of arc. They combined that with a careful estimate of the star's distance, about 3,900 light-years. From these two measurements, the apparent size in the sky and the actual distance, they could calculate the real physical radius. The number they arrived at was 0.420 solar radii, give or take about 120. This was, at the time, one of the most carefully measured radii for any red supergiant. The error bars are still significant, but they are smaller than the error bars on most other stars in the same size range. VY Canis Majoris, when you ask astronomers which red supergiant is the best characterized, comes up often as the answer. It is the one we have measured most carefully. It is the one whose radius we trust most. The star is also dying in the slow way that red supergiants die. VY Canis Majoris is shedding mass at a rate that is, by stellar standards, enormous. The outer layers are streaming away from the star in a steady wind, dense with dust and molecules. Around the star, observable in radio and infrared telescopes, there is a vast cloud of ejected material, gas that VY Canis Majoris has thrown off over the past few thousand years. The amount of mass in that cloud, by some estimates, is on the order of 10 times the mass of the Sun. 10 suns worth of material, already cast out, drifting slowly outward into the surrounding interstellar medium. The mass loss is not steady. It comes in bursts, in irregular ejections, in plumes that astronomers can image with high-resolution telescopes. Some of these plumes have been traced to specific years, specific events. The star is, in a sense, falling apart in slow motion. Not collapsing, not yet, but shedding itself layer by layer into the surrounding dark. When VY Canis Majoris finally does collapse, in some thousands or tens of thousands of years from now, he will go either as a supernova or, possibly, as something stranger. Some models suggest that very massive stars at the end of their lives may collapse directly into black holes without an explosion, simply winking out instead of going bang. VY Canis Majoris is large enough and massive enough that either outcome is possible. We do not know which it will be. We do not know when it will happen. But it will happen. Take a breath. Settle in. The star is dying, slowly, 3,900 light-years away. Its light, as you watch this, has been travelling toward us since around the year that Augustus became Emperor of Rome. By the time you see anything new from VY Canis Majoris, we will all have been gone for many human lifetimes. That is one star, and VY Canis Majoris, the star with the 6-hour photon, the star that would swallow Jupiter, the star whose ejected nebula contains 10 times the mass of the Sun, is still not the largest one we have measured. There is at least one star that is larger, and in November of 2024, for the first time in the history of astronomy, that largest star was photographed up close. That is where we are going next. There is a particular detail about VY Canis Majoris that, when you understand it, helps explain why this star is special even among red supergiants. VY Canis Majoris sits very close, in physical terms, to a theoretical limit. The limit is called the Hayashi limit, after a Japanese astrophysicist named Toshiro Hayashi, who worked out the relevant physics in the 1960s. The Hayashi limit is the maximum size a cool star can have given its temperature and luminosity. Beyond a certain radius, a red supergiant's outer layers become so unstable that they cannot remain bound to the star. The gas blows away. The star, in a sense, hits a wall. The Hayashi limit for stars in the temperature and mass range of VY Canis Majoris sits somewhere around 1500 to 2000 solar radii. VY Canis Majoris, with its 1420 solar radii, is right at the limit. This is not a coincidence. It is a statement about what the star is doing. VY Canis Majoris is, by every measurement, pushing against the boundaries of what red supergiant physics allows. The star is so distended, so swollen, so close to the upper end of stable size, that any further expansion would tear it apart. The mass loss we observe, the cocoon of gas around it, the dust shells in its surroundings, are all signs that the star is operating at the edge of its own structural integrity. This is part of why VY Canis Majoris is famous. It is one of the clearest examples we have of a star sitting at the Hayashi limit. The fact that we've measured it carefully enough to know this, and the fact that its measured radius lines up with the theoretical prediction, is one of the success stories of stellar physics. It also tells us something useful for the rest of our journey tonight. If the Hayashi limit caps red supergiants at around 1500 to 2000 solar radii, then any claimed measurement significantly above that range needs to be treated with skepticism. Stars cannot, by current physics, be much larger than this and remain stable as red supergiants. The 2150 solar radii estimate for Stephenson 2118 sits right at the upper edge of what is physically possible. The 2000 solar radii estimate for WOH G64 sits within the limit. Stars claim to be 3000 or more solar radii, like some old estimates of VB Cephei from the mid-20th century, are almost certainly wrong, because they would violate the Hayashi limit. The physics of these stars, in other words, places its own constraint on the size question. No matter how interesting a measurement looks, no matter how exciting a new candidate is, the laws of stellar structure tell us roughly where the ceiling is. The largest possible red supergiant cannot exceed certain bounds. The current record holders are pressing right against those bounds. This is, in a strange way, comforting. The competition for largest known star is not unbounded. It is approaching a real physical ceiling. We may, in fact, already know stars that are within 10 or 20% of the absolute upper limit. The remaining uncertainty is large, but it is not infinite. We are not searching for stars 100 times larger. The candidate stars in our top tier are all within roughly the same range, because that range is the range that physics permits. The biggest known star may be within striking distance of the biggest possible star. On a working day in late 2024, in a control room at the European Southern Observatory's facility in Chile, a small team of astronomers were processing data. The data had been collected over several nights using an instrument called gravity, mounted on a system called the Very Large Telescope Interferometer. The target of the observations was a single star, a star nearly 2,000 times the size of the Sun, a star far beyond our own galaxy. The data was being assembled into an image. Astronomers do not, usually, take pictures of stars the way you would take a picture of a friend. Most stars in the sky are too far, too small in apparent size to be resolved as anything other than points of light. We can record their brightness. We can measure their spectra. We can infer their properties from indirect signals. But to actually image the surface to see the disk of the star itself is rare. It has only been done, with current technology, for a handful of stars in our own galaxy. Betelgeuse is one, Antares is another. Mira, the variable star in Cetus, is another. A few others. The list is short. Before November of 2024, every star ever imaged in this way had been in our own galaxy. Then, on the 21st of November, the European Southern Observatory released a press image. It was small. It was grainy. To the untrained eye, it looked like a smudge. An oval blob, slightly elongated with hints of structure inside. The kind of image that, in a different context, you might not look at twice. But the smudge was a star, and the star was in another galaxy. The star is called WOH G64. The name comes from a 1981 catalogue compiled by 3 astronomers named Westerlund, Olander, and Hedin. The W, the O, and the H are their initials. G64 is the catalogue entry number. The star sits in the Large Magellanic Cloud, a small companion galaxy of our own Milky Way. The Large Magellanic Cloud is the brightest of our satellite galaxies. From the southern hemisphere, on a dark night, you can see it with your naked eye, a faint pale smudge that looks like a small detached piece of the Milky Way drifting in its own corner of the sky. The Large Magellanic Cloud is about 160,000 light-years away. That is far, very far. Our galaxy itself, from one side to the other, is roughly 100,000 light-years across. So the Large Magellanic Cloud, while it is a companion of our galaxy, gravitationally bound to us, is more than a galaxy's width away in distance. Inside that distant satellite galaxy, embedded among hundreds of millions of other stars, sits WOH G64. It has been known to astronomers for decades. It is one of the largest known stars in the Large Magellanic Cloud. Its size has been estimated, from indirect measurements, at roughly 2,000 times the radius of the Sun. That is larger than VY Canis Majoris. That is larger than any star whose radius has been well measured in our own galaxy. But for decades, even though we knew approximately how big WOH G64 was, we had never seen it. We had only seen the light it emitted, collected into a single point by our telescopes. We had measured the spectrum of that light. We had inferred from the spectrum the surface temperature. We had inferred from the brightness combined with a distance, the luminosity. From the luminosity and the temperature, we had calculated the radius. The chain of inference was solid, but it was inference. No human had ever looked at WOH G64 and seen anything other than a point. To resolve the star, to actually see its disk, required an instrument that did not exist for most of the decades during which WOH G64 was being studied. The instrument that finally did the job is called gravity. It is a second-generation instrument at the Very Large Telescope Interferometer. It combines the light from 4 separate telescopes, each 8 meters across, using a technique that allows the combined system to behave, for purposes of resolution, like a single telescope much larger than any of its component parts. Gravity can resolve detail at angular scales smaller than 1 millisecond of arc. That is 1,000th of a second of arc. That is the kind of resolution that, applied to the right targets, can begin to show the disks of distant stars. In 2024, a team led by an astronomer named Keiichi Ohnaka of the Universidad Andrés Bello in Santiago, Chile, decided to point gravity at WOH stellate 64. Ohnaka had been studying this star for nearly 2 decades. He had used the VLTI on it before in 2005 and 2007 with earlier generation instruments. He had published papers on its properties. He was patient. He waited for the instrument that could do what the others could not. When gravity became available, when the observing time was approved, when the conditions were right, his team made the observations. The result was the smudge. The smudge that, when you understand what you are looking at, is one of the most extraordinary astronomical images of the 21st century. In the image, there is a bright oval at the center. The oval is not a clean disk. It is more like an egg than a circle. The longer axis of the oval is slightly elongated compared to the shorter axis. Around the bright oval, there is fainter structure, a kind of ring or partial halo. The whole thing covers an angular size on the sky, smaller than you can imagine. If you held a coin out at arm's length, the angular diameter of WOH G64 in the image would be tens of thousands of times smaller than the coin. But the image exists, and what the image shows is the dust-shrouded surface of a star in another galaxy. For the first time in the history of astronomy, a star outside our own Milky Way has been resolved as more than a point of light. We have seen it, up close. In a single image, Ohnaka and his team published a paper in the journal Astronomy and Astrophysics, volume 691, article L15. The image, and what it implies about the star, became one of the highlight scientific results of the year. Take a breath. Stay with the image for a moment. What we are looking at when we look at that smudge is the surface of a star nearly 2,000 times the size of the Sun. A star in a satellite galaxy of our own, a star 160,000 light-years from Earth. A star whose light, by the time we see it, left its surface around the time the last Neanderthals were still alive. We are looking through a chain of telescopes and instruments and human patience that took decades to build at a thing no human had ever seen before. A face, the face of one of the largest stars we have ever measured. And it is, even at this resolution, mostly mystery. Let us spend another moment with that image, because in the months and years to come, that image will be referenced in textbooks and documentaries and articles. It marks a real boundary in what astronomy can do. Until November of 2024, every star ever resolved as more than a point was inside our own galaxy. That fact, simple as it sounds, was one of the basic constraints on what we could see of the wider universe. We could measure stars in other galaxies through their combined light, their statistics, their broad properties, but we could not look at one specific star far away in another galaxy and see anything other than a contribution to a galactic blur. That changed with WOH G64. The change is not just a technical milestone, it is a window into what is now possible. The same technique that produced the WOH G64 image, interferometry with G-gravity, can in principle be applied to other large, luminous stars in nearby galaxies. The Andromeda Galaxy, the most famous of our neighbours, sits at about 2.5 million light-years away. That is roughly 15 times further than WOH G64. The largest stars in Andromeda are, in theory, candidates for similar imaging, though the work would be even harder. Other satellites of our own galaxy, smaller and closer, host their own giant stars that might be reachable. The 2024 image, in other words, is a beginning. It is the first photograph of a star outside the Milky Way. It will not be the last, and in the case of WOH G64 specifically, the image carries some particular surprises. Astronomers had known about WOH G64 for decades. They had measurements of its luminosity, its temperature, its inferred radius. The expected appearance of the star, modelled from all of this indirect information, was a roughly spherical object surrounded by a roughly spherical cocoon. The image, when it arrived, showed something different. The cocoon is not spherical. It is elongated, egg-shaped. The asymmetry was not predicted by the simple models. It is a real feature of the data, and it tells us that whatever is going on at WOH G64 is more complicated than the simple models assumed. This is, by the way, how astronomy makes progress. You build a model, you make predictions, you observe, you discover that the observations do not match the model, you adjust the model, you observe again. The cycle continues. Each adjustment brings the model closer to the actual physics. The 2024 image of WOH G64 is one such adjustment moment. The simple models did not predict an egg shape. The data shows an egg shape. Now we have to figure out why. The leading candidates for the asymmetry are, as we mentioned, internal convection and a possible companion star. Both are interesting. Both are observable in principle through different techniques. The next few years of observation will probably tell us which one is right, or whether the truth is some combination of both. In the meantime, the image sits in the European Southern Observatory's public release archive. Anyone can find it online. Anyone can look at it. The smudge, the egg, the faint hints of a halo. The first picture of a star outside the Milky Way, a thing humans had never seen until late one year in the early 21st century, when a small team in Chile finally put together the right combination of telescopes and patience. We do not, as a species, often look at images like this one. The internet floods us with new images every day. Most of them are forgotten in hours. The image of WOH G64, in its quiet way, is the kind of image that will outlive most of them. It is a record of a moment when humanity reached, for the first time, beyond its own galaxy, to look at a single object. If you want to see it for yourself, look up the European Southern Observatory's release dated November 21st, 2024. The image is there. It looks like a smudge. It is in fact the surface of a dying star in another galaxy. 2,000 times the size of the Sun, 160,000 light-years from your eyes. Let us stay with the image for a few more minutes, because the image, when you read it carefully, tells more than one story. The bright oval at the center is not a clean disk of a star, it is instead a dusty cocoon, a shroud of material that the star itself has produced and is producing now. The star hidden inside is shedding mass into space. The mass condenses as it cools into tiny grains of solid dust. The dust accumulates around the star in a thick veil. What gravity sees in the image is not the photosphere of WOH G64. It is the cocoon of dust that wraps around the photosphere. The star, in other words, is so hidden by its own shed material that even when we resolve it for the first time, what we see is not really the star. We see the cloud the star has made of itself. This is not a small detail. It is part of what makes WOH G64 so interesting. The cocoon means the star is losing mass, not gently, not in the long, slow stellar wind of a stable red supergiant. The mass loss is faster than that, much faster. The cocoon is thick. It is opaque to most of the visible light the star produces. From Earth, before the 2024 image, what we saw of WOH G64 in optical wavelengths was not the star directly, but the diffuse flow of light that had managed to leak through or around the cocoon. Some of the brightness we measure from WOH G64, even today, is light that escaped the cocoon from the back of the star and somehow worked its way out to us. Some of it is light that was absorbed by the dust and re-radiated in infrared. The chain of light from the photosphere of the star to the detectors of our telescopes passes through a thick layer of self-made dust before it gets out. The cocoon is also strangely shaped. The image shows it as an oval, not a sphere. Elongated. Egg-shaped. That is unusual. Stars, especially old massive ones, are usually approximately spherical. A spherical star shedding mass evenly should produce a roughly spherical cocoon. WOH G64 is not doing that. The mass is being lost more strongly in some directions than in others. Why the asymmetry? There are two main ideas. The first is that the mass loss is being shaped by the star's own internal convection. Red supergiants have enormous convective cells, regions where hot material from deep inside is rising to the surface, while cooler material is sinking. These cells can be enormous. Some of them, in stars this size, can be comparable in scale to the orbit of Jupiter. Convection on this scale is not uniform. It produces bright spots and dark spots. It produces at the surface regions of unusually strong outflow and regions of relative calm. The cocoon, if shaped by convection, could be uneven because the underlying mass loss is uneven. The second idea is more dramatic. There may be a companion star. WOH G64 may not be alone. Some recent observations have suggested that the star may have a stellar companion, gravitationally bound, orbiting somewhere in the cocoon. If a companion exists, its gravitational pull would shape the mass loss in specific ways. Material being shed by WOH G64 would be channeled toward the companion, or thrown outward in particular directions by the orbital motion. The cocoon, if a companion is shaping it, would be egg-shaped for the same reason the wake of a boat is asymmetric. There is a second object in the picture. Even if we cannot see it directly, we do not know, as of this writing, which of these explanations is correct. It may be both. It may be neither. The image gives us hints. The data so far is consistent with multiple stories. More observations are being planned. The honest answer is that the asymmetry is real. The explanation is still uncertain, and the next decade of work on WOH G64 will probably resolve the question. There is something else in the data, something that has been observed and discussed, but not yet fully understood. WOH G64 has been growing dimmer. Over the past decade or so, since the early 2010s, observations of the star have shown a slow decrease in its visible brightness. The star is fading by amounts that are noticeable to careful astronomers, but that would not be visible to the naked eye, even if WOH 64 were close enough to see, which it is not. The dimming is real. It is steady. It has been going on for years. The leading interpretation is that the dimming is caused by the cocoon itself. As the star produces more dust, the cocoon thickens. As the cocoon thickens, less light escapes. The star is, in a sense, slowly burying itself in its own shed material. Each year, a bit more dust, a bit more opacity, a bit less light reaching Earth. If this is correct, then the dimming is not the star itself getting fainter. The star is fine by stellar standards. It is the veil between us and the star that is getting denser. The star, if you could look through the cocoon, would look much the same as it did a decade ago. The cocoon is what has changed. What this dimming means for the future of WOH G64 is one of the most discussed open questions in this corner of stellar astronomy. Red supergiants do, eventually, end their lives. Most of them go as core collapse supernovae, the core having burned through hydrogen, then helium, then carbon, then oxygen, then neon, then silicon, finally reaches iron. Iron cannot fuse to release energy. The core, no longer supported by fusion, collapses under its own gravity. The collapse takes a few seconds. The shockwave that follows blows the outer layers of the star into space, leaving behind a neutron star, or, if the star is massive enough, a black hole. The whole event, the supernova, briefly outshines the entire galaxy in which the star sits. WOH G64 will do something like this, probably. The most likely fate, based on what we know about its mass and its current stage of life, is some kind of core collapse event. But the timing is genuinely uncertain. The mass loss we are seeing, the cocoon we have just imaged, the dimming over the past decade, all of these are consistent with the star being in a late stage of its evolution. Some astronomers have suggested it is in what is called a superwind phase, the very last stage before the core collapse. If that is correct, the supernova could be relatively close in astronomical time, perhaps within thousands of years. Others have looked at the same data and proposed that the star may have already moved past the red supergiant phase entirely into something called a yellow hypergiant phase, with a smaller radius and a hotter surface than typical red supergiants. A paper by Munoz-Sanchez and collaborators in 2024 made this argument. They suggested the star may have shrunk to about 800 solar radii and heated up substantially, becoming a yellow hypergiant rather than a red one. More recent work by Van Loon and Ohnaka in 2026 looked at spectroscopic data taken between 2024 and 2025 and found molecular absorption bands of titanium oxide. Titanium oxide is a signature of red supergiants. Its presence argues that WOH G64 is still a red supergiant after all, contrary to the yellow hypergiant claim. The debate is active. The papers are being written now. We do not know with any certainty what stage of life WOH G64 is currently in. We do not know when it will supernova. It could go in our lifetimes. It could go in 10,000 years. It could go in 100,000 years. The honest answer is that for any single dying star, the timing of the final explosion is not predictable to better than thousands or tens of thousands of years. The star is preparing. The cocoon is real. The mass loss is happening now. The supernova is somewhere in the star's future, and somewhere in our future too. But the exact when is something the universe has not chosen to tell us yet. What we can say is that when WOH G64 does finally go, the event will be visible from Earth. The supernova, at a distance of 160,000 light-years, would be one of the brightest events in the night sky for months. It would briefly outshine the entire Large Magellanic Cloud. It would be visible during the day. People all over the southern hemisphere would see it without telescopes. But by the time we see that event, the actual explosion will have happened 160,000 years earlier. WOH G64, if it goes tonight, has actually already gone, in any meaningful sense. The light just has not arrived yet. The star may have ended long ago, while we sit watching as preserved light and imagining a future that has, by the universe's clock, already become the past. If you have spent any time reading about the largest stars on the internet, you have almost certainly come across the name Stephenson 228. It is by far the most popularly cited candidate for the title of largest known star. It appears in countless videos, articles, listicles, and educational materials. Its size, given in those sources, is usually quoted as 2,150 times the radius of the Sun, That number, 2150, is repeated so often that it has acquired a kind of internet truth. People say it because other people have said it. The chain of repetition has become its own evidence. But the truth about Stephenson 2218 is more complicated and more interesting than the popular story. The star was discovered, or more accurately catalogued, in 1990 by an American astronomer named Charles Bruce Stephenson. Stephenson was working on a survey of bright infrared sources in the southern sky. He was looking for clusters of red supergiants, regions where massive stars had been born together in dense groups and were now reaching the late phases of their lives in close proximity. One of these clusters, near the constellation Scutum, became known as Stephenson 2. Inside that cluster, Stephenson catalogued a number of individual stars, numbered Stephenson 2 to 1, Stephenson 2 to 1, and so on. The 18th star in the cluster was Stephenson 2 to 18. For nearly 2 decades after Stephenson's original work, the cluster sat quietly in the astronomical literature. It was studied by various groups. Distance estimates were refined. The members of the cluster were characterized in various ways. None of this work made Stephenson 218 famous. The fame came in 2012. In that year, a team of astronomers led by Beverly Fock of the University of Hong Kong published a study of the Stephenson 2 cluster using data from the Australia Telescope Compact Array, combined with a kind of stellar atmosphere model called dust-Y. The model is designed to handle stars surrounded by, you guessed it, dust. Red supergiants, like the ones in this cluster, tend to be wrapped in dust shells of their own making. To measure their fundamental properties accurately, you need a model that accounts for the dust. Fock and colleagues, applying dust-I to Stephenson 218, derived a radius for the star at 2,150 solar radii. That number, when it was published, was unprecedented. It would make Stephenson 218 larger than any other star whose radius had been formally measured, larger than VY Canis Majoris, larger than WOH G64, larger than every other known candidate. If correct, Stephenson 218 was the new champion, but there is a critical assumption baked into the calculation. The radius depends on the distance. The further away a star is, the larger it has to be to produce the brightness we see. The Fock 2012 paper used a distance to Stephenson 218 of approximately 6 kiloparsecs, or about 19,000 light-years. That distance was based on the assumption that Stephenson 218 is a member of the Stephenson 2 cluster. The cluster's distance has been measured by various means, mostly through the average properties of its many member stars. If Stephenson 218 is in the cluster, its distance is approximately the cluster's distance, and the 2,150 solar radii estimate follows. But is Stephenson 218 actually in the cluster? That turns out to be a serious question. Stephenson 218 sits in approximately the same direction as the Stephenson 2 cluster. But same direction does not mean same distance. Stars can appear close together on the sky while being at very different actual distances. The line of sight from Earth runs through many regions of the galaxy, and stars in the foreground can look, projected onto the sky, like they belong to a more distant group when they do not. Several subsequent studies have looked at Stephenson 218 carefully and asked whether it really belongs to Stephenson 2. The answers have been mixed. Some analyses, including more recent ones, have suggested that the star's properties are more consistent with being a foreground object, somewhat closer to us than the cluster proper. If Stephenson 288 is a foreground star, its distance is less, and its radius, calculated from its observed brightness, would also be less. Substantially less. How much less is the question. Different studies have produced different revised numbers. Some have brought the radius down into the range of 1500 of 1600 solar radii. Others have brought it down further, to perhaps 1,000 or even less. The honest summary as of the early 2020s is that astronomers do not agree on Stephenson 218's distance, and as a result they do not agree on its size. This is not a failure of astronomy. It is in fact astronomy working as it should. A bold claim was made. The claim was based on assumptions. The assumptions were scrutinized. The community is now in the process of refining the answer. Through more observations, more analysis, and more careful reasoning about cluster membership and distance, What this means for the title of largest known star is that Stephenson 218, despite its internet fame, is not a settled answer. The 2150 solar radii number that gets quoted everywhere is the original 2012 estimate based on a specific distance assumption that may or may not hold up. The star may indeed be that large. It may be somewhat smaller. It may be considerably smaller. We do not yet know with confidence. This is also, oddly, what makes Stephenson 218 a useful object to study. It is a star at the limit of what our current methods can measure. The difficulty of pinning down its size tells us about the limits of our techniques. Every refinement, every new measurement, sharpens the question. The honest answer today is that Stephenson 218 might be the largest star we have measured. It also might not be. Both options are still on the table. For comparison, WOH G64 in the Large Magellanic Cloud has been imaged directly and has a radius measurement of about 2000 solar radii based on multiple independent observations across many years. The radius is not perfect either, but it is more directly anchored. The distance to the Large Magellanic Cloud is one of the best-known distances in extragalactic astronomy, refined over decades. Stephenson 218's distance, by contrast, is contested. When astronomers list the largest known stars today, the responsible ones list both candidates. WOH W64 and Stephenson 2288 are typically both mentioned, sometimes alongside several other contenders like NML Cygni, RW Cephei, and VV Cephei A. The list itself is the answer. There is no single name at the top. The wonder, in some sense, is not that we cannot pick a winner. The wonder is that we have measured any of these stars at all. We are talking about objects 10 to 20,000 light-years away, in some cases more, with surfaces that have no clear boundary, hidden in dust, embedded in clusters whose membership is debated. That we can measure them within 20 or 30% of their actual size is an achievement. That we can argue about which is largest is a sign of how far stellar astronomy has come. It is worth understanding for a moment why cluster membership is such a critical question. Because the issue with Stephenson 218 is not unique to this one star. It is a recurring problem across all of stellar astronomy. When astronomers look at a region of sky and identify a cluster of stars, they are working from indirect evidence. Stars that appear close together on the sky are not necessarily close together in space. They might be at the same distance, gravitationally bound, sharing a common origin. They might also be at completely different distances, simply lined up by chance from our viewing angle. To decide whether stars belong to the same cluster, astronomers use a combination of clues. Stars that form together tend to share certain spectral signatures, reflecting the chemistry of the gas cloud they came from. They tend to share certain motions through the galaxy, because they were all born moving in roughly the same direction. They tend to share ages because they all started fusion at roughly the same time. If all of these clues line up, the stars are probably in the same cluster. If they do not line up, the stars are probably not. For most of the cluster Stephenson 2, the membership analysis works reasonably well. There are many stars in the region. Their properties cluster. They share approximate distances, approximate ages, approximate compositions. The cluster, as a cluster, is real. The trouble is with the individual outliers. Stephenson 218 is, in some analyses, exactly the kind of outlier that might or might not belong. Its properties, when measured carefully, do not perfectly match the average properties of the cluster as a whole. The differences could be explained by Stephenson 2218 being a slightly unusual member of the cluster, or they could be explained by Stephen S10 2288 being a foreground star closer to us, that happens to appear projected onto the cluster from our viewing angle. Different teams have looked at the available data and reached different conclusions. Some argue strongly that Stephenson 218 is a member. Others argue strongly that it is a foreground object. The argument has been going on for more than a decade now. It will probably continue for some years yet, until enough new observations accumulate to resolve the question. This is what active science looks like. It does not always look like a settled answer. Sometimes it looks like a long, careful argument between people who are looking at the same data and seeing different things. Both sides are doing their best. Both sides have reasonable interpretations. The truth in cases like this takes time to emerge. For our purposes tonight, the relevant fact is simply that the question is open. Stephenson 218 might be the largest star ever measured, with a radius around 2,150 solar radii. Or it might be substantially smaller, in which case some other star, perhaps WOH G64, holds the title. Either possibility is consistent with what we know. Neither has been definitively settled. Compare this briefly to a well-measured nearby star. Sirius, the brightest star in the night sky, has a radius known to better than 1%. We know the distance to Sirius to better than 1 part in 10,000 because the parallax is enormous and easy to measure. We know its surface temperature from spectroscopy. We know its mass from its orbital motion with its companion Sirius B. Everything about Sirius is, by stellar standards, almost certain. For Stephenson 218, none of these things are almost certain. The distance is contested, the temperature is hard to measure because of dust extinction. The mass is unknown to within a factor of several. The radius depends on all of these in a chain of inference that can produce very different answers depending on which assumptions you make. This is the difference between studying a nearby star and studying a distant, dust-shrouded, contested cluster member. The nearby star is easy. The contested cluster member is hard. The fact that we have any radius estimate at all for Stephenson 218 is a triumph of modern astronomical technique. The fact that we cannot pin it down to within 30% is not a failure. It is a reflection of how genuinely difficult the measurement is. Take a moment to picture, in your mind, a tennis ball. You know exactly where the edge of the tennis ball is. The fuzzy yellow surface ends, and the air begins. If you wanted to measure the radius of the ball, you would use a ruler. You would put the ruler against the surface. You would read off the answer. Now picture a candle flame. The flame is hotter and brighter at the center. It fades to softer light at the edges. You can see the flame. You can see roughly how big it is. But if someone asked you to measure the radius of the flame to within 1/10 of a millimeter, you would not know where to put the ruler. The flame does not have an edge. It has, instead, a region where it gradually becomes less bright, less hot, less there. The boundary is fuzz. It is gradient. It is not a line. A red supergiant is much more like a candle flame than a tennis ball. This is the first reason measuring a star is hard. Stars do not have surfaces in the way solid objects do. The outer layers of a red supergiant are extremely thin gas. The density drops off gradually, over a region that can extend for hundreds of millions of kilometers. There is no place where you could put a foot. There is no place where you could put a ruler. There is only a slow, soft fade from somewhat thicker gas to thinner gas to nothing at all. Astronomers, when they need a number for the radius of a star, have to pick a definition. They have to choose, somewhere in that gradient, the place they will call the edge. The standard choice is the radius at which the gas becomes thin enough to be transparent to most light. That is a real definable point called the photospheric radius. But it is not the only choice you could make, and different observation techniques, sensitive to different wavelengths of light, can give you slightly different answers for where that edge is. Different definitions, different numbers. All correct in their own way. None of them quite the same. That is one problem. Here is the second problem. When you look at a star in the sky, you are not seeing the star directly. You are seeing the star through whatever is between it and you. The space between stars is not empty. It contains hydrogen, helium, dust, and stray particles. Dust is the main culprit. Tiny grains of carbon and silicate scattered through the galaxy intercept some of the light traveling toward us from distant stars. The dust absorbs some of the light. The dust reddens what is left. The dust, in some directions, blocks the view almost entirely. Stephenson 218, the star we just discussed, is hidden behind a lot of dust. So is most of the inner Milky Way, the bright central regions of our galaxy, where many of the most massive and largest stars are believed to live, are obscured behind clouds of intervening material. We cannot see directly into the heart of the galaxy in visible light. We see only what poke through in patches between the clouds. This means that any measurement of a distant star's brightness has to be corrected for dust. We have to estimate how much light was absorbed on the way to us, and add it back in to figure out how bright the star actually is. The correction is sometimes small. Sometimes it is enormous, and the correction is not perfect. It is a model based on assumptions about how much dust is between us and the star, what kind of dust it is, and how it absorbs light at different wavelengths. If the dust model is off, the brightness estimate is off. If the brightness estimate is off, the radius estimate is off. The chain of inference is only as good as its weakest link. Take a breath. The journey is long. We are nearly through the difficult stretch. Here is the third problem. Even after you have picked a definition of the star's edge, and even after you have corrected for dust, you still need to know the distance to the star, because the apparent size of a star in our sky depends on two things: how big the star actually is, and how far away it is. A larger star far away A larger star far away can look the same as a smaller star nearby. Without the distance, we cannot disentangle the two. For nearby stars, the distance is measured directly through parallax. As the Earth orbits the Sun, our viewing angle on a nearby star changes slightly. The star appears to shift back and forth against the background of more distant stars. The size of that shift, the parallax, tells us the distance. It is the same trick your eyes use every moment of your life to give you depth perception. Two viewpoints, separated by a known distance, looking at the same object. The angles tell you how far away the object is. The European Space Agency's Gaia mission, launched in 2013, has measured the parallaxes of more than 1 billion stars with extraordinary precision. For nearby stars, Gaia has given us distances accurate to fractions of a percent. This is why UY Scuti got demoted. Gaia measured the distance more accurately. The previous distance estimate had been too large. With the corrected distance, the radius came down. But Gaia's reach is limited. Parallax depends on having two viewpoints, separated by a known distance. Earth's orbit gives us a baseline of about 300 million kilometers. That is enormous on a human scale. It is tiny on a galactic scale. For very distant stars, the parallax angle becomes too small to measure, even with Gaia's precision. Beyond a few thousand light-years, parallax distance becomes unreliable. Beyond 10,000 light-years, it becomes nearly useless. Stephenson 218 is 19,000 light-years away, if it is in the cluster. WOH G64 is 160,000 light-years away. These are far beyond Gaia's effective range. For these stars, we have to use other distance methods. Cluster membership, spectral signatures, standard candles. These methods are less direct. They have larger uncertainties. They contribute their own errors to the radius estimate. Here is the fourth problem. Even when you have all of these things in hand, the apparent size of the star in your telescope is incredibly small. The angular size of a star, the size it appears in the sky, is measured in milliseconds of arc. A second of arc is 1/3600th of a degree. A millisecond is 1,000th of that. We are talking about angular sizes, smaller than the size of a coin held in the palm of someone standing in another country. To resolve such a small angle, you need a telescope much larger than any single optical telescope ever built. You need a telescope with an aperture, the size of its main mirror, of hundreds of meters. Such telescopes do not exist and probably cannot be built on the ground. The way around this is interferometry. If you have multiple telescopes spread out across a large area, you can combine their light. The combination, when it is done well, behaves like a single telescope as large as the spread between the individual ones. The Very Large Telescope interferometer in Chile spreads 4 8-meter telescopes across about 100 meters. The combined system has the resolution of a 100-meter telescope, which is much, much sharper than any individual 8-meter telescope could ever be. This is how WOH G64 was imaged. Interferometry. 4 telescopes in Chile, combining their light into a single virtual telescope. The G-Array Vidi instrument, second generation, designed specifically for this kind of work. Ohnaka's team, waiting for the right moment, the right conditions, the right alignment of equipment and patience. That is the technology that finally let us see a star in another galaxy as more than a point, but even that technology has limits. Interferometry is hard. It requires perfect alignment of the contributing telescopes to within fractions of a wavelength of light. Atmospheric disturbance, vibration, temperature changes, all of these can corrupt the measurement. The technique only works for the brightest, biggest, closest targets in their respective categories. WOH G64 was at the edge of what is currently possible. Stars further away, smaller in apparent size, or both, are still beyond our reach. The biggest star in the universe, if it exists somewhere in another galaxy at 1 billion light-years distance, is invisible to us. Not just unmeasured. Invisible. We cannot resolve its disk. We cannot even, in most cases, separate its light from the galaxy it lives in. That, in the end, is the deepest answer to why measuring a star is so hard. Most stars are too far. Most galaxies are too distant. Most of the universe is, even today, blurred into smudges and points of light. We measure what we can. We are honest about what we cannot. Now we come to the question I have been holding back all the way through this journey. The question that, if you sit with it for a moment, is the strangest part of the whole conversation. Every star we have discussed tonight is in our own galaxy. Every single one of them. Betelgeuse, Antares, Mu Cephei, VY Canis Majoris, Stephenson 218, even the various contenders we mentioned in passing. All of these are stars in the Milky Way. The single exception is WOH G64, and WOH G64 is in the Large Magellanic Cloud, a small companion galaxy gravitationally bound to our own. From the perspective of the universe, the Magellanic Clouds are essentially our backyard. Now consider the universe at large. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. The number depends on how you count, what you include, and which decade's measurements you trust. But the order of magnitude is solid. We are part of a system of hundreds of billions of stars, all gravitationally bound, all orbiting the galaxy's center, all sharing this one enormous structure. The observable universe contains hundreds of billions of galaxies, each one containing on average somewhere between tens of millions and trillions of stars. The total number of stars in the observable universe is, by current estimates, on the order of 10 to the 23rd, or possibly more. That is a 1 followed by 23 zeros. It is a number that does not mean very much when you write it down. The human mind cannot really hold a number that large. Among all those stars, somewhere is the biggest one, the biggest red supergiant or red hypergiant in the entire observable universe. The single largest star that physics allows to exist, sitting in some galaxy, at some distance from us, going about its long, slow life. We have no idea where it is. We have no idea what its name would be because no one has catalogued it. We have no idea what its radius is because no one has measured it. We have no idea what galaxy it lives in because most galaxies are too far for us to resolve individual stars at all. The biggest star in the universe is almost certainly a star humanity has never seen as anything other than blurred light from the galaxy in which it lives. This is not poetic exaggeration. This is the honest scientific situation. Of those hundreds of billions of galaxies, we have catalogues of bright stars only for the very nearest ones. Our own galaxy, the Magellanic Clouds, M31, the Andromeda Galaxy, 2.5 million light-years away, M33, the Triangulum Galaxy, a handful of other nearby spirals and dwarfs. Beyond that, individual stars in other galaxies are usually beyond the reach of current instruments. For most of the universe, we cannot see individual stars at all. We see only their combined light, summed up across an entire galaxy. The galaxy itself is a smudge in our telescopes, even with our best instruments. The stars inside it are simply contributions to that smudge. You cannot, with current technology, point at a particular pixel in an image of a distant galaxy and say that is one star, that is another, and there are the largest ones. You can only say the galaxy has so much total light, so much total mass, so much total age. The individual stars are blended into a statistical average. This means the biggest known star, the one we have measured, the one we have actually catalogued, is bound by selection. We can only know about stars we can see. We can only measure stars whose properties we can disentangle from the background of other stars near them on the sky. Out of the 100 sextillion or so stars in the universe, we have measured the radii of perhaps a few thousand. Out of those few thousand, the largest is whatever the current consensus says. It is, almost by definition, not the largest star in the universe. It is the largest star we have happened to measure. The biggest star in the universe, by reasonable statistical argument, is in some galaxy we have barely catalogued, at some distance we cannot resolve, in some patch of sky we have looked at only briefly. If at all, it is there. It exists. It is going about its life, shedding mass, pulsating, preparing for its eventual end. It is doing all of this without our knowledge, without our names, without our measurements. It is, in the most literal sense, the biggest star in the universe, and we will, in any practical sense, never see it. Take a breath. Stay with this for a moment. That is the deepest part of the answer to tonight's question. The biggest known star is not the biggest star. The biggest known star is the biggest one we have happened to look at carefully enough to measure. Our knowledge here is a tiny corner of the actual landscape. The universe is vast. Our catalogues are small. The gap between them is enormous. There is a kind of humility in this, a useful one, perhaps. The largest objects in the universe are, almost certainly, things we will never name. They are things that exist beyond our reach, doing what they do, regardless of our attention. Our measurements catch only the closest, the brightest, the ones that happen to be in our line of sight. The rest is dark. The rest is unmapped. The rest, in some way, will always be unmapped, no matter how good our telescopes become. This is not a sad thing. It is, in its own quiet way, a beautiful thing. The universe is more full than we can ever measure. There are more giants than we can ever name. The list of the largest stars will keep growing every few years as new measurements push the frontier further out. But the actual largest, the true champion of cosmic size, is somewhere we are not looking, and it does not care. Let us spend another quiet moment with this idea, because it is the deepest part of tonight's answer. There is something specific worth saying about why our knowledge of distant stars is so limited. Even the closest galaxy outside our own backyard, the Andromeda Galaxy, is 2.5 million light-years away. That distance, 2.5 million, is roughly 15 times further than the Large Magellanic Cloud, where WOH G64 lives. Andromeda is much further. And Andromeda is, in galactic terms, our next-door neighbour. In Andromeda, we can detect individual bright stars in some cases. The brightest red supergiants in Andromeda are visible to large telescopes as resolved points of light. Their distances are reasonably well known. Their basic properties can be measured, but we cannot with current technology image their disks. We cannot do for an Andromeda red supergiant what we did for WOH G64. The Andromeda stars are too far. Their angular sizes are too small. Even the most advanced interferometers today cannot resolve them. The same is true, even more strongly, for galaxies beyond the local group. The local group is the small cluster of galaxies to which the Milky Way, Andromeda, and a few dozen smaller systems belong. Beyond the local group, galaxies are typically tens of millions of light-years away, or more. At those distances, individual stars are completely lost in the combined glow of their host galaxies. We see a galaxy. We can study the galaxy as a whole. We cannot see its individual stars at all. This is not a small limitation. It is the central constraint on what we know about stars in the universe. There are perhaps 200 billion galaxies in the observable universe. Of those, we have meaningful individual star catalogues for, generously, 2 or 3, the Milky Way, the Magellanic Clouds, maybe Andromeda with limitations. Beyond that, our knowledge of stars in other galaxies is statistical. We know the typical properties of stars in a galaxy from its overall light. We know that big galaxies have more stars and small galaxies have fewer. We know that older galaxies have redder stellar populations on average. We can guess at how many giant stars exist in a given galaxy, but we cannot name them. We cannot measure their individual radii. We cannot pick out the largest one in any given galaxy and study it. Think about what this means for our search for the largest star. If we assume that the formation of red supergiants and red hypergiants follows roughly the same statistical rules everywhere in the universe, then every massive galaxy contains stars in the same general range of properties as our own galaxy's giants. Some of those galaxies, by simple statistics, will contain stars at the extreme end of the size distribution. Some will contain stars larger than anything in our own galaxy. Some will contain stars at the absolute upper limit of what physics allows. We cannot see any of them. The largest star in any single distant galaxy is, in the truest sense, invisible to us. Its light blends into the galactic background. Even if we knew it existed, we could not separate its individual contribution from the contributions of the millions of other stars in that galaxy. It is a mathematical reality, supported by every model of stellar formation. But it is, observationally, gone. When we say the biggest star in the universe is one we will never see, we are not being poetic. We are stating a real constraint on observational astronomy. The universe is so large and so full of stars that the absolute extreme of any property, the brightest, the largest, the most massive, is almost certainly somewhere outside our reach. We see only the closest examples. We measure only what falls within our limited radius of detail. This is, in some ways, the most important thing the question of largest known star can teach us. The known is not the actual. The measured is a tiny corner of the existing. Our catalogues are bright spots in a much larger landscape of unseen things. There is a phrase, sometimes used in astronomy, called Malmquist bias. It refers to a specific statistical effect where the stars we see in our catalogues tend to be the brighter ones simply because brighter stars are easier to see at greater distances. The result is that any catalogue, no matter how carefully assembled, is biased toward bright objects. The full population of stars at any distance includes many fainter ones we miss. The same principle, in a slightly different form, applies to size. The largest stars are easier to see because they are also typically luminous. We are not missing them entirely, but we are missing the ones that are far enough away that even their light cannot reach us in a form we can resolve. The actual largest star, the one that physics permits, is almost certainly in some galaxy where its light is mixed with the light of 100 billion others, and we will not, with anything like our current methods, ever pick it out. This is not pessimism. It is simply the honest description of where the limits of measurement currently sit. The universe is, in every direction, full of objects we have not measured. The largest of every category, the brightest of every category, the most extreme of every category, are probably out there beyond our cataloguing reach. We work with what we can see. We learn what we can. We acknowledge what we cannot. And every so often the technology improves enough to expand the reach a little. November of 2024 was one such moment. We crossed for the first time the boundary of our own galaxy in the imaging of an individual star. Future moments will extend the reach further. Maybe one day in some far future of astronomy, we will resolve individual stars in galaxies tens of millions of light years away. Maybe we will find in those galaxies stars larger than anything yet measured. Or maybe not. Maybe the limits of our technology will stop somewhere short of that. Maybe the absolute largest star will remain, forever, beyond our reach. Either way, it is out there. It exists. Statistical reasoning, applied to the formation of stars across the universe, tells us it must. We do not know its name. We do not know its constellation. We do not even know its galaxy. We only know that by every physical argument we can make, the actual largest star in the universe is real and is somewhere and is doing what it does and will probably never be measured by anyone on Earth. Take a breath. Let that sit for a moment. We have travelled in our minds across an enormous landscape tonight. We started with our own sun, a photon circling the surface in 14.5 seconds. We moved to Betelgeuse, the red shoulder of Orion, the star you can see from your own backyard. We climbed through Antares and Mu Cephei. We met VY Canis Majoris, where the same photon would take 6 hours to make the same trip. We crossed into another galaxy and looked at WOH G64, the first star outside our Milky Way ever to be resolved as more than a point. We touched on Stephenson 2218 and its contested radius. We talked about why measuring a star is harder than it sounds. We sat with the strange truth that the actual biggest star in the universe is somewhere we will never see. That is a long road. If you have walked it with us all the way to this point, thank you. Here is what I want to leave you with before you sleep. The list of largest known stars will change again. Some new instrument, some new technique, some refinement of distance or interpretation will move WOH G64 down or up. Some other candidate, perhaps in a galaxy we have not yet examined closely, will rise into the top tier. The next decade of astronomy will bring new measurements, new arguments, new contenders for the title. Whatever name is at the top of the list right now will, probably, not be at the top of the list 10 years from now. It is the nature of this corner of science. The frontier moves. That is not a problem. It is not a failure. It is what science is. A long, slow, patient correction of yesterday's answers. A list that grows. A picture that sharpens. And underneath all of this argument, underneath all of the catalogue numbers, and the contested distances and the dust models and the spectral analyses, there is something simpler. We have built telescopes that can see across galaxies. We have, in November of 2024, photographed the face of a star in a different galaxy from our own. We have measured, with reasonable accuracy, the sizes of stars so large that light takes hours to travel around their surfaces. We have done all of this from a small rocky planet around the small ordinary star, on the outskirts of a fairly typical spiral galaxy in an unremarkable corner of the universe. It is, if you think about it, an astonishing thing to have done. The list of biggest stars matters less than the fact we have a list at all. The argument about whether Stephenson 2218 is bigger than WOH G64 matters less than the fact that we can argue. The uncertainty is a sign that we are looking. The shifting answers are a sign that we are still learning. Right now, in your room, somewhere on a quiet planet, you are connected to all of this. The sun warmed your day. The stars are over your roof, even if you cannot see them through the ceiling. WOH G64 exists 160,000 light-years away, going about its long, quiet decline. Its light, by the time we see it, left the star before any human writing was invented. Betelgeuse hangs over the winter sky, with its photons arriving from before the Mongol conquests. VY Canis Majoris dies slowly, 6 hours of photon travel around a single surface. All of them are part of the same universe you are in. The same physics. The same patience. The biggest star we have measured is not the biggest star in the universe, but it is, for now, the biggest we know. And the wonder is not in the name. The wonder is that we know it at all. Take a breath. Let your shoulders drop. The stars are still there, very far away, doing what they do. We do not need to hold them in our minds tonight. They will be there tomorrow, and the night after, and for many lifetimes after that. Sleep well. The biggest star you have heard of tonight will not be the biggest you hear of next year. And that, in its own quiet way, is the best part of the answer. The list will keep changing. The stars themselves will not. They are out there now, somewhere in the dark. Larger than you imagined. Larger than anyone has yet measured. Larger than anyone will measure for a long, long time. Larger still than your imagination.